Physics 2212 Lab 3, Magnetic Field of a Bar Magnet, presented by Kenneth Alexander Jenkins for Fall 2023. Introduction, Purpose. To measure and compare the distance dependence of a small bar magnet's magnetic field with theoretical predictions based on the Biot-Savart law. Fundamental principles. Magnetic field of a dipole, listed below, where r is the observation location and micro u is the magnetic moment, as well is the magnetic field of a bar magnet listed as below. It is important to note that we will be using the natural log in order to break apart this function for easier graphing. Brief results are listed below. Introductions, models, and assumptions. Models and assumptions. For this lab, the bar magnet is treated as modeled as a dipole for the purposes of calculations in order to apply the Biot-Savart law. Definitions of systems and surroundings. Systems is the bar magnet, and surroundings is the meter and everything else. Listed on the right is the magnetic field lines, which we will be graphing. Experimental procedure, step 1, finding the magnometer chip. Step 1, the phone is lined up on the meter stick with the physics toolbox app open. It is slid around until the magnometer is pinpointed in the horizontal axis. Step 2, the location of the magnometer is marked with a piece of tape in the horizontal axis. Step 3, the phone is lined up on the meter stick but is rotated 90 degrees until the magnometer is pinpointed in the vertical axis. Step 4, the location of the magnometer is pinpointed and marked as the location in which the phone has the strongest recorded magnetic field. Step 2, using the magnometer chips, recorded values on the axis component. The on-axis distance from the bar magnet to the magnometer was calculated using the provided spreadsheet. These values were linearized by taking the natural log of both sides, as seen below, and graphing them. On the right, you can see the listed results, the measured distances, as well as a graph. Experimental procedure, step 3, finding the values of the off-axis component. The off-axis component was calculated using the recorded values and the provided spreadsheet. Listed above, you can see a graph of what we are trying to graph, a diagram of what we are trying to graph, as well as below, seeing the calculated results using the measured values. Here, you can see the code. I've also listed the code below. This code was provided using starter code. However, I will just be stepping through what I've changed. To the left, you can see the final calculated result as well as the calculated products. And on the right, you can see what I've changed. I've tried to mark as much as I can. Here, you can see on line 25, I've added previous calculated values. And on lines 33 through 37, I've added a function to create a magnetic field. Then, I've also fixed the scale and added previous recorded values, as well as creating magnetic dipole errors and added magnetic field dipole errors. It is important to note that these were provided in the sample code and then just changed slightly in order to fix what the necessary instructions wanted. Then I added the previous calculated values for the distance perpendicular, as well as added the perpendicular dipole arrows below. These are the calculated results in their entirety. Here's the what if and why questions. What if you hadn't orientated your experiment to compensate for magnetic north and instead had tried to lay out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? The magnetic fields would be different since we weren't compensating for magnetic north. This is for both the x and y components and would likely increase. However, the z component would likely not be affected since the magnometer would be laid flat. What if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your experiment to differ? The magnitude would likely increase since the magnetic fields of both magnets would combine. However, the measured distances between the magnetic fields would likely decrease due to the increased magnetic field magnitudes from both magnets. Lab questions. Which of these statements correctly describe what you've observed? I don't know if this can show up too well, but it's 1, 2, and 3. When the magnometer is far away from the magnet, it measures at a near zero magnetic field in the x direction. And as the magnometer moves closer to the magnet, the measured x component of the magnetic field decreases, as well as the position of the magnometer has no effect on the measured x component of the magnetic field. Similarities and differences. Modeling discrepancies. A bar magnet's field typically models very closely to the models of that of a magnetic dipole, so our choice of model is likely yielding very accurate results. There were no noticeable differences between calculated results and observed results. Conclusion. Potential sources of error: electronics emitting magnetic fields, inconsistent placement of the phone, along with software distortion of the physics toolbox app, and measurement errors and inconsistency in surface flatness. This is for the z component. Conclusion. Both the Biot-Savart law and distant dependencies can be applied to a bar magnet with fairly accurate results using computational models. Bar magnets can be used accurately to model magnetic dipoles, and distance is incredibly important when determining the strength of the magnetic field.